Sure. So my speak for today about the KD-type theorem for the sigma group. So first I would like to say I thank you and appreciate to Dr. Heisenauer to be my advisor and help me and guiding me to do the research projects. So it's the KD-type theorem for my for the sigma group is the one of the thing in my research project is about the fundamental theorem for sigma group, and I found out the KD-type theorem which is interesting, and I would like to talk for today. So first, let me give the definition about the sigma group. So sigma group is the branch of the algebraic structure, and it's along with the group theory, ring theory, field, and vector space, and some others. So here the definition for the sigma group. Let S be a non-empty set and star be an associative binary operation on set S. Then we say S star is a sigma group. So by the definition above, we know that the set S is said to be a sigma group, then S must satisfy two axioms, closure and associative. The closure means for all element A and B in the sigma group S, A star B also in S, and associative. That means A star B and then star C is equal with A star, the composition between B star C for all of A, B, and C in the sigma group S. And here is some example about the sigma group. The set of the integer number, the rational number, the real number, and complex number under the addition is from the sigma group. So in the multiplicative case of those sets, one may remove the zero elements from the domain and still obtain a sigma group. In the case, if a sigma group S had the identity element which is number one, and sigma groups will become a monoid. In the case, if the monoid have the inverse element, it will become the group. And here's the clear definition about the monoid. So let S be a sigma group if S contains an element 1 with the property that for all A in S, A times 1 equal with 1 times A equal with A. We say that 1 is an identity element of S, and S is now called a sigma group with identity or a monoid. The set of the integer under the multiplication is a monoid with identity number 1. And like I said earlier, if the monoid have the inverse element, we have the definition for a group. Like if the sigma group with the identity number 1, so it's called a monoid. And if it have inverse element A inverse for all A, such that A times A inverse equal with A inverse times A equal with number 1, which is the identity element, so that is called a group. And the set of the integer under the addition is a group. Next, I will talk about like the sigma group homomorphism. So just like a study in group homomorphism, we have the same definition for the sigma group homomorphism. And here the definition. A map theta from the sigma group S into sigma group T is called a homomorphism if for all S and Y in the sigma group S, such that theta of S times Y equal with theta S and composition theta Y, where theta S, theta sub S, and theta sub Y in the operation of the sigma group T. So that is the definition of sigma group homomorphism. Thus, a homomorphism respects the product of the sigma group S while transferring the element to T. Since we are working on the sigma group in general, so S does not necessarily have identity because by the definition of sigma group. But if S is a monoid, which is the have the identity number 1 right now, then the homomorphism will map the identity element of the first monoid to the identity element of the second monoid. For me, I feel that's really important because I will apply that to prove the KD theorem for sigma group later. And by the definition of sigma group, it just only have the two properties, that is closure and associated. But in the group theory, for the definition for group, it have the 4 probabilities. This is closure, associative, It has identity and inverses. Therefore, the group is the subset of sigma group, and between the group and sigma group, they have the something connection, and also it have the different. And the Cayley theorem will be tell us how they are different and how they are similar and how they are different, how they have the connection. So let's take a look for the Cayley theorem for the group. It says every group is isomorphic to a permutation group. It has the two concepts in the theorem. It is isomorphism and permutation of the set. So the isomorphism means it exists a homomorphism function that is the one-to-one and onto. And the permutation of the set, it exists a one-to-one corresponding, which is the one-to-one and onto function, where all the elements from that set is mapping into itself. So take on of the element, let's say theta is the permutation of the group from the group G to G. It is one-to-one and onto. So it maps all of the elements from that set into itself, and it must be the one-to-one and onto function. That's how the definition of the permutation of the set. And thus, I will wonder about, does the Cayley theorem apply to the sigma group? Since the group is a subset of sigma group, so does the Cayley theorem apply to the sigma groups? So in the other way, can we say every sigma group is isomorphic to a permutation sigma group? Well, to make it clear about that, there are two things I need to worry about. First, it is the isomorphic. The second is the permutation sigma group. Can we say the permutation sigma group? And the answer is yes, we can say that. But however, in general, sigma group doesn't necessarily have identity or inverse element. So instead of saying the permutation of sigma group, and also the sigma group arise from more general mappings of the set into itself, not really mean the one-to-one and onto. Therefore, we have a new definition for that. It's called the full transformation sigma group. And that is the definition. So let F be a non-empty set. A full transformation sigma group in S is the collection of map of the set S into itself, which is flow under the operation of composition of the function. And it denoted by the tau S. Thus, the tau S did the necessary to be the one-to-one or onto. And now I can say the Cayley theorem for sigma group in the better way, like every sigma group is isomorphic to a transformation sigma group. So for the word permutation sigma group, I already dealing with, and instead of saying the permutation sigma group, I'm using the new definition. It is transformation sigma group, and to make the Cayley theorem much better and it's suitable for saying for the sigma group, since sigma group it less the property than the group. And now the other word I need to dealing with it is isomorphic. When I say every sigma group is isomorphic to a transformation sigma group, that means there exists a homomorphism function from the sigma group S into the full transformation sigma group tau S that is one-to-one and onto. And let we see this function right here, that theta from S into the full transformation C tau S, the function right here, it has the definition for that. So let theta be a homomorphism from the sigma group S into the full transformation sigma group tau S, such that theta from S into tau S. Then theta is called the representation of S. So I define the new name for the homomorphism function theta from the S into the tau S. It is called the representation of S. Okay, and now does the theta can be the one-to-one and onto? Well, in the case to make the theta become the one-to-one, let's say if I am adding the identity element number 1 into the sigma group, and then sigma group will become the monoid because it has the identity right now. And by the definition of the homomorphism of monoid, like I said earlier, if the monoid have, if the sigma group have the identity, that means it will be mapped the identity of the first monoid into the identity of the second monoid. So that means the function the function theta from the sigma group S to the full transformation sigma group tau S, it can be the one-to-one. But what about with the onto part? Well, If we think about the onto part, that means the semi-group S it has the invert element. But if we add the invert element into the semi-group S, and currently right now the semi-group only become the monoid because I only add number 1 into the semi-group S to make it become the monoid. So if the monoid have the invert elements, so that means it will become a group, and therefore the Cayley theorem just apply for the group, like what I already learned in the abstract algebra in group theory. So therefore, it didn't necessary to say theta can be the onto, because if it's onto, it should be become a group. The sim group can become the group, and then Cayley theorem just directly apply for the group, and then for sim group it doesn't have nothing mean with it. So therefore, it's not necessary to say the theta from the S into tau S can be the onto. And we happen, and thus right now the theta, the E to call the representation of S, and if it have the 1-to-1, so it will become the have the new definition for that, and it is called the faithful representation of semi-group, which means if theta from the S to tau S is 1-1, then theta equal the faithful representation of semi-group. And thus the Cayley theorem for semi-group can be said every semi-group has a faithful representation. So I only dealing with isomorphic and the permutation semi-group. Thus here the Cayley theorem for semi-group. Every semi-group has a faithful representation. And here the proving of the Cayley theorem. So here my group for the Cayley theorem in the semi-group. And thus we can see that I add the number 1 into the semi-group S to make it become the monoid, and that's the reason for me group theta can become the 1-to-1. And then I define 2 maps. The first one is the rho A sub S equal with AS, and the second one is the theta of A equal with rho A, and then I can show it become theta E 1-to-1 and theta E the homomorphism. So after I prove theta E the 1-to-1 and homomorphism, so that means the Cayley theorem for semi-group was proven. Yeah, it's proved. And the result from the study the semi-group for Cayley theorem semi-group. So in group theory, the Cayley theorem enable us to view the groups as the group of permutation of some set. The analogous result in the semi-group theory represents semi-groups as the semi-group of functions from a set into itself. Therefore, the theory of semi-groups can be learned by study of transformation. So that's the important thing I get it from the research about semi-group. The theory of semi-groups can be learned by study of transformation. And that's the end of my speak for today. So thank you so much, and I wish us all the best and have the great conference today. Thank you.
Thank you. Let's thank Luan.